Okay, so we're going to finish up our notes on work energy. And so here we are at 9.6 in the work energy theorem. Excuse me. So whenever work is done, energy changes. And so you can think of it like these guys, they just did a lot of work and now they have very little energy. So they used up their energy in doing that work. So in formula form, that's work is equal to delta change in kinetic energy. So here I have that if you push an object at a constant velocity, there is no change in kinetic energy. And there's no change in the kinetic energy because the velocity is not changing. So if you think about something that is moving at a constant velocity, if its velocity is constant and its mass is constant, then it is not changing its kinetic energy because Ke equals 1/2 mv squared. So that's the why not. If you need a change in its mass or a change in its velocity in order to get a change in kinetic energy. So kind of same thing here is that if this guy's just holding this boulder, yeah, his muscles are doing work because they're contracting and softening, but the rock isn't moving. So if it's not moving, he's not doing work. Therefore, there's no change in energy in this rock. If this guy runs along at a constant speed, then he is not doing work because he is keeping the same kinetic energy. If he's accelerating, then he is doing work because he is changing his velocity and therefore is getting a change in kinetic energy. And then so some other examples, a guy is swinging the baseball bat, hits the baseball. It does have a change in velocity because it's going one way and then it goes the other way. So that change in kinetic energy is going to be equal to the work done by the bat on the ball. The car over here, it skids to a stop. And in so doing, it's changing its velocity. Therefore, it's changing its kinetic energy. And whatever change in kinetic energy is going to equal to the work that was done on the car by the brakes of the car and skidding to a stop. Okay, so we have the car to the right took 100 meters to stop. If it had been going twice as fast when slamming on the brakes, how long a distance would have been needed to stop and why? Okay, so first off, we're going to say that our kinetic energy, Ke, is equal to 1/2 mv squared. And that is going to be equal to force, that's an F, sorry, force times distance, which is equal to work. So we have our kinetic energy is equal to 1/2 mv squared, and that is equal to the force times distance, which is equal to work. So it's just saying changing kinetic energy here is equal to work over here. And then we have our formulas, 1/2 mv squared equals force times distance. Okay, so we're going to plug in some numbers here. And I'm going to try to use some easy numbers. So we're going to try to find our kinetic energy of that car when it was moving along. So we're going to say it's 1/2. Let's say its mass is 1,000 kilograms. So 1,000 times its velocity. Let's say its velocity was 10 meters per second. And then we square that. Okay, and then that is going to be equal to the force times distance. But let's solve this out first. So we have 10 squared, which is 100. 100 times 1,000 is 100,000. And 1/2 of 100,000 is 50,000 joules of kinetic energy. And that is going to be equal to the force times the distance. Well, the distance we already said was 100 meters right here. So if we have 100 meters as our distance, our force would have to equal whatever, it's like x times 100 equals 50,000. This over here needs to be 50,000. Okay, so what times 100 equals 50,000? 500. So we have 500 newtons of force acting for 100 meters equals 50,000. And again, that is joules. Okay, so then we're going to Okay, so now we are going to say the car is going twice as fast. So we are going to use this same formula right here. 1/2. The mass did not change, so that will still be 1,000 times the velocity, which instead of 10 will now be 20 squared. And then so we'll have 20 squared is 400. 400 times 1,000 is 400,000. And half of 400,000 is 200,000 joules of energy. And that is going to equal to our force times our distance. We're going to assume that our force is the same for the brakes, so 500 newtons times the distance, which we're going to put in here, is going to be equal to the 200,000 joules of work. And then so 500 times what is going to give us 200,000? And the answer is 400 meters. Okay, so there's our answer. That at first it took 100 meters to stop. When we doubled the speed, it now takes 400 meters to stop. So one way of thinking about this is if you double the speed, so it's 2 times what it was, 2 squared is equal to 4. And that 4 is the 4 times the distance that you'll need to stop. This is one of the reasons you shouldn't really tailgate somebody. And the faster you go, the more space you need to allow somebody in front of you. So if I were going, or if this car were going 3 times faster, how would that affect the stopping distance? Well, I don't have to go through all of this. I can just say, well, 3 squared equals 9, and that's 9 times the distance. If it was going 4 times faster, 16 times the distance, so on and so forth. Okay, so now we're on to the conservation of energy. And the conservation of energy is something you probably all have heard of before and hopefully have a good understanding of it. And that is that energy cannot be created or destroyed, but it does transform from one form into another. So for instance, you put your batteries into a little toy thing that makes it go. So the chemical potential energy in the battery can be transformed into sound energy if it makes noise, or it can be transformed into kinetic energy if it rolls around, so on and so forth. But the total energy remains constant, and that is really important to understand. So if we look at this picture over here, the basketball that is bouncing, theoretically, if you drop a ball, it should bounce to the same height you dropped it from, and each time it should bounce back up to that same height. That is not what we see. And the reason we don't see that is when you bounce the ball here, the ball makes a sound. Sound is energy. So energy is being lost from the system. It's not lost in total, but it is carried away. And therefore, the energy that goes into sound does not go into moving the ball back up. Also, when it bounces, it compresses. And when you compress things, they heat up. And so there's actual heat generated here, which also takes away from the ability of the ball to bounce higher. So each time it bounces, it goes through these processes where it gives off sound and heat is generated, and so it doesn't bounce as high. And so eventually it will stop bouncing, and you would think, oh, it lost all that energy, but it didn't lose the energy. The energy was just transformed into something else. Same goes for your roller coaster. The first hill of the roller coaster is the biggest one, because energy, and if you can't see me, I'm making the quotation marks with my hands, is lost. It's not lost, it's transformed into sound energy of the cart going down the roller coaster. It's transformed into heat. The wheels on the roller coaster warm up as it moves along. And so these hills get progressively smaller and smaller as the roller coaster goes through. So again, theoretically, whatever the potential energy of the roller coaster is at the top of the hill should be transformed into kinetic energy, which is equal to the potential energy at the bottom of the hill. And then it goes back and forth. So as you're up here, you have a lot of potential energy. As you get down here, that potential energy is transformed into kinetic energy. And then that kinetic energy goes back into potential energy and back and forth, kind of like a pendulum that swings back and forth as well. So this idea carried forward, so perpetual motion, this idea that You could hold a magnet in front of this car and the magnet would pull the car forward. This just doesn't exist because energy is always transformed into wasted energy, and that gets into something we call efficiency. And we'll talk about that as we do our potential energy cars whenever we return from this break. Okay, so the idea of making the most efficient car is great, but we can never attain 100% efficiency. So energy is always transformed into waste energy, such as heat and sound. And so again, usually that waste energy is thermal energy or sound. You drive your car for a while, you come back home, and you notice that the car is warm. Okay. And then so that takes us into our potential energy cars. And so when we get back from break, these are what we'll be building. And so you can make like a fan car, you can make a mousetrap car, or these are called gravity cars. Either way, you need to do work to the car. In this case, with the gravity car, you lift a weight, which means you're doing work to lift it up here. And then as the weight falls back down, it will transform that into kinetic energy of the car. Over here, you need to wind the fan. You're doing work to turn this, which will then be stored as potential energy and then converted to kinetic energy when you let go. With the mousetrap, you pull back the trap. That is doing work. So you're putting work in so it can have stored potential energy. And then when you let go, it will propel the car and turn that into kinetic energy. And again, hopefully we'll be back soon and we can start building these.